Right. Our next speaker is Andrey Prokopenko from ORNL, and the title is Scalable Geometric Search Algorithms in ArborX.
Thank you for inviting me to speak in this session. This is going to be a slightly different talk from the previous ones. It has very little to do with linear algebra. Rather, it is going to be devoted to the geometric search algorithms. And in Oak Ridge, we developed a library called ArborX that does just that for HPC applications. And of course, one of the questions is, why is it called ArborX? And having two French-speaking developers means that tree in French is arbor. So this is why the library is called ArborX. OK, so I don't know how many people are actually familiar with what geometric search is, but in general, geometric search the goal is to find objects in space that are close to your targets in some sense. In our work, we have several applications. One of them is coming from the wind technology application, where you have multiple moving meshes, and at each time point, you have to interpolate some data from one mesh to another. And to do that, you need to understand which cells of one mesh overlap with cells of the other mesh. And this is a way to do that. But it's also used in many other applications. I'm not going to go into detail. And of course, as having in the whole DOE complex devoted to exascale, it has some requirements on it to be distributed parallel, have good performance, and support multiple supercomputers with multiple architectures. We wanted to offload some of that hard work to other people, so we chose Kokkos, as many people do, so that we don't need to worry about so much about hardware requirements, and we can devote our resources to more on the distributed side and algorithmic side. And people already went through what Kokkos is, but it's essentially on-node backend for us. So there are a bunch of different ways you can do geometric search. A lot of people use KD trees. A lot of people use R trees. They're similar. They're different in some ways. For us, our main thrust was to use GPUs. And one of the best and most efficient algorithms on GPUs was developed by KNearest back in 2012. And it was based on a bounding volume hierarchy. Bounding volume hierarchy is a tree where essentially you bound given set of geometric objects with some kind of bounds. Usually it's axis-aligned bounding boxes because they're cheap and easy to compute. And then you construct a tree by merging together and constructing larger bounding boxes. This is a brief, kind of concise representation, and where your stick figures are your objects. Then we form the bounding boxes and we construct the tree. I'm not going to go into too many details on how we do that, because that's not the focus of this talk. But in order to improve the performance of all these trees, we actually need to understand which objects are close to each other so that we can form the hierarchy the right way. And one of the ways to do that is to linearize the whole space of geometric objects by using space-filling curve. In our case, we use Z-curve, which is based on Morton codes. And it kind of looks like on the top right, a figure where you go through the space, you do the Morton codes, and you sort them. So briefly, the bounding volume hierarchy is constructed in 5 steps. So first of all, a user provides us with geometric objects, and either the user provides us with bounds, or we construct them ourselves based on some function. For each box that we constructed, we choose the centroid, and then we compute the Morton code for that. We sort them to improve the locality and to linearize the whole space of the objects, and then we construct the tree fully in parallel. And that's the key point of the KNearest work, where he demonstrated that it is possible to construct it fully in parallel on GPU instead of going level by level, which is too slow. Originally, it was developed for the GPU rendering of the collision when you in video games, when the stuff flies around and you need fast intersections. And then once you have the hierarchy, you need to actually compute the bounding boxes of each node of the hierarchy, and that's done also in parallel. Now, there are two very distinct search capabilities that may be required to do on such in geometric search. And one of them is spatial search, or rather the predicate search. A lot of people know that how essentially you try to find all the objects within radius r of your point, and how many you find, that's your answer. And this is a specific case of a more general predicate where you have some function, and for every point you say either yes or no results. It's kind of predicate. The challenge with this is mostly on GPU because you don't know how many results it will produce before you actually run it. And because dynamic allocation are kind of a pain on GPUs, we typically either run it twice, where the first run we count the number of objects, and then the second time we actually store them, or we require users to provide us with an strict upper bound on the number of found objects so that we can pre-allocate the storage and to store them using a single pass. And the second search is different. It's mostly known as KNearest Search, where you find k closest objects to a given target. And here is, in some ways, it is easy because you only need, you exactly know the upper bound on the number of found objects. It's k, so you can pre-allocate the storage. You don't need to tweak how many passes you do. You just need to do a single pass. And there are some performance tweaks that you can do, but not going to go there. This slide simply says that even in serial, the developed library that the ArborX beats well-known libraries such as, I don't know how many people know, but Nanoflan is a widely popular library. And Boost Geometry also provides R3 implementations. And we beat them in serial, and of course, ArborX supports both CUDA, OpenMP, and that runs a lot faster. Anyway, so going back to the distributed search, now the interesting part starts. So in distributed setting, it's not, you have data partitioned between different processors. So each processor constructs its own tree, which we call the bottom tree, which is local tree. And then on top of that, we construct a distributed tree, which is replicated among all the processors, where the leaves of that tree are the bounded boxes for the processor domains. And right now, the upper tree is also BVH tree, but it doesn't have to. And we are investigating other trees for performance, because the difference between the bottom tree and the upper tree is the size of the tree. The bottom tree is based on the number of objects that the user provided, while the upper tree is actually limited by the number of ranks you run your code on. So if you run somewhere on Summit and you use a single MPI rank per node, you just have 4,000 leaf nodes, which is a pretty small and may not be perfect for the BVH tree. Construction is actually pretty easy in the sense of the communication. It requires a single MPI all-to-all to exchange the bounding boxes among all the processors. Now, the search part is interesting. Generally, you have queries on each processor, but you may also get valid results from other processors that may have some contributions. So your first step would be to identify the processors that could produce non-empty results. And then you do send local queries to those processors, perform local searches for combined queries, and then return the results and merge them together. And generally for spatial search, this is where it ends, because for spatial search, you know exactly which domains your radius will overlap. And so you know exactly the ranks you need to send your queries to. For the nearest search, it is harder. So you could theoretically say that, well, I have to search for k equal to 100. So I guess I'll choose the 100 closest processors, and I'll send all my queries to those 100 processors. I'll do the search and then combine results, but that sounds really expensive. So instead we do 2 passes, but I'm also not sure if that is the best way. So if anybody knows how to do proper KNN in distributed setting, I would be very glad to talk to you. But right now what we do is we do the first pass, we try to find the processors that could give us a reasonable number of results, of reasonable results. So what we do is we first find the KNearest trees, but then we accumulate the leaf nodes from each tree until we reach that K number. So theoretically, if your domain size and if the number of objects per domain is large enough, you can just be limited by a single tree. So what you would do is, in that tree, you search for K neighbors, and then you choose the distance to be equal to the distance to the furthest of that K. And then based on the distance, you choose the number of processes to actually do the exact determination in the second pass. And that is typically a lot less than if you send it to all K nearest local trees. We have some scaling. I actually didn't put too many results in. We ran it on Summit nodes. And on the left figure, we have about 1 million. I forgot to change. Actually, it's 1 million objects per tree, and we search for about 100,000 objects up to 6,000 nodes, which is about a quarter of Summit. And generally, and this is weak scaling. Now, generally it scales okay, but we also found that scaling from one GPU to 2 GPUs to 3 GPUs to 6 GPUs doesn't scale well. It's when you go beyond one node. So if you take node as your baseline and then you scale beyond that, everything looks pretty stable. But it's the on-node scaling with MPI just doesn't scale well for some reason, and we are looking into that. And on the right, we have a lot less values and queries per GPU, which emphasizes the communication more rather than GPU work. And you see that KNN actually increases, but the other two stay pretty stable. So the part that I'm really excited about, and which just recently introduced in this work, was user-provided callbacks. Now, imagine a situation where you have a mesh which is partitioned among all the processors. So that mesh is pretty heavy object. And typically, when you do search, you may not want just the results. You may want some function of the results. So you don't want to do, well, I computed all the results, I did all the communication, but now I have to communicate also mesh data and some other data for me to actually do stuff that I care about. In that case, we may want to provide the user with a way to do something on that processor that already has all the data so that it doesn't have to communicate back. And our way of doing that is to provide 2 types of user callbacks. The first callback is when you traverse the tree and you want to actually insert the result into the final output. We provide the function for user to override, where user may specify, first of all, what it wants to insert, and second, whether a user wants to insert at all. So you can think of, for example, one of the very useful use cases for this one, if you want to do a find search. So if you want to, for example, for your point to find the mesh element that the point belongs to, first you do the coarse search with the bounding boxes, and then inside the callback, you can actually do the find search using the geometric data of the mesh to actually figure out whether there is intersection or not. And we provide the insert, but we don't specify what insert is. You just need to either call it or not call it with your data. We also have a functionality to attach the data to the queries. It can be some global ID or some other data, and in the MPI context, that data will be also distributed along with the queries. The second type of callbacks is called not when the data is inserted, but rather once all the data is inserted, but it's still on the processor local storage. You can run a different kind of parallelization algorithm on all the results on that processor before combining it back. This is also common in situation where you have different kind of mesh elements and you want to group them by all triangles, all the hexes, whatever, and then do parallelization based on that. And we implemented those callbacks, and so for spatial searches, they work just fine. And mostly this is a property of the fact that for spatial searches, you always get the correct results, and all the results are then combined using a simple union operation. You don't need to do any filtering, so all the results are valid. For the nearest, we discovered after we implemented and wrote the test that actually nearest are really hard, and we don't know how to properly do them yet. And the challenge with the nearest callbacks is the fact that all the processes will compute some data. For example, you search for 10 points, you send your queries to, I don't know, however many processors, each of them produces 10 points, 10 results, but then you need to combine those, I don't know, 100 results into 10 based on the distance. However, if you allow user to call the callback, you may lose information. You may lose the correspondence of the result to the distance that produced that result. And it is totally unclear how to combine the data if we allow a generic callback for a user. So right now, we actually disabled all of that for the nearest callbacks because we don't know how to properly do that yet. Anyway, so this is kind of the summary. I guess there's no summary, there's just future. So what we are looking forward to is we want to implement the oriented bounded boxes, and that is really important for our application. So in the wind technology application, we have moving meshes, but the meshes are weird in the sense that they have the wind turbine blades, which are very stretched and non-axis aligned. So if you surround them by bounded box, the actual mesh takes a very small fraction of the box itself, which has performance implications in distributed sense. We are also looking at the compressing data structures. For right now, we implemented everything in doubles, but we are looking at floats, and then we also may look beyond floats to quantized packing, so that to minimize the memory bandwidth. As I mentioned, we look at the brute force search for the top tree and nearest callbacks. Anyway, that's all I have. Thank you.